Whenever we read, speak, or listen, we experience language strictly as a sequence in time. One word comes after the next. For a long time, this was exactly how neural networks handled text. Architectures like recurrent neural networks, or RNNs, read sentences one discrete token at a time. They maintained a running hidden state, a kind of mathematical memory that gets updated with every new word. But there is a fundamental problem here. Time is a bottleneck. Because the network must process word 49 before it can process word 50, it cannot take advantage of modern, highly parallel computing. Worse, by the time the network reaches the end of a long paragraph, the mathematical memory of the very first words has become smeared out and diluted by all the intermediate updates. The memory fades. In 2017, a landmark paper proposed a radical shift. What if we break free from time entirely? Instead of feeding words in one by one, the transformer architecture ingests the entire sequence all at once. Every discrete token is simultaneously mapped into a high-dimensional space. Suddenly, our chronological sequence of words transforms into a constellation of vectors, processed perfectly in parallel. But this introduces a rather glaring issue. If everything is processed simultaneously, if there is literally no longer a mathematical concept of before or after, how does the network know how these words relate to each other? How does a disconnected bag of isolated vectors capture the rich, interconnected structure of human language? To see why it is so useful to process all words simultaneously, let's look at a fundamental problem in language: ambiguity. Consider the sentence, "the bank of the river." If we just look at the word bank in isolation, what does its vector look like? In a standard static lookup table, bank is assigned a single fixed coordinate. In our space, this generic embedding might sit awkwardly halfway between a cluster of finance-related concepts and a cluster of nature-related concepts. It doesn't inherently know which one it is. But in a transformer, words don't live in isolation. This is where the magic of self-attention comes in. Imagine a web of connections forming between every word and every other word in the sequence. They are all looking at each other. Through this web, words essentially ask their neighbors for context. In our example, bank looks around and notices the word river. The network has learned that river is highly relevant here, so this specific connection lights up. Mathematically, river passes a bit of its own vector's meaning over to bank. As it does, watch what happens to the vector for bank. It physically shifts. It moves away from the financial cluster and deep into the nature cluster. It's no longer just a generic bank. It is now a highly specific, context-aware vector representing a riverbank. This, at its core, is self-attention, a mechanism that allows words to dynamically update their own mathematical meaning by absorbing the context of their surroundings. To make this mechanism mathematically precise, transformers borrow a concept from database retrieval: queries, keys, and values. Think of how a search engine works. You type in a query, what you're looking for. The database checks your query against its keys, the invisible tags describing each file. If the query and the key match, the system hands you the value, the actual document. In a transformer, every single word acts as all three of these things simultaneously. We start with our original word embedding vector. The network multiplies it by three distinct weight matrices, projecting our single word into three new vectors: a query, a key, and a value. Let's look at the word bank. It needs context, so it uses its query vector to essentially ask, are there any water-related words around? Down the sentence, the word river holds up its key vector, which translates to, I am a body of water. To measure how well they match, the network calculates the dot product between bank's query and river's key. Geometrically, this just measures how aligned the two vectors are. A high positive dot product means a strong match. If we compute this dot product for every possible pair of words in our sequence, we get a grid of raw attention scores. But these raw scores can be unruly, some huge, some negative. So we pass each row through a softmax function, which elegantly squishes the scores into clean percentages that sum perfectly to 1. Finally, we use these percentages to mix together the value vectors of the words. If river scored 85%, we take 85% of its value vector, maybe 5% from the and 10% from bank itself, and add them all together. This resulting weighted sum is the context update. We add it directly to the original bank vector, shifting its position in high-dimensional space squarely toward the concept of water. So far, we've looked at attention as a single operation. A word sends out one query, compares it to everyone's keys, and creates one updated value. But think about how complex language really is. In the sentence, "The fluffy dog chased the fast cat," the word dog is doing multiple things at once. It's the noun being modified by Fluffy, and it's also the subject performing the action chased. If we only have one set of queries and keys, the network is forced to average all these different relationships together. It has to compromise. The solution is surprisingly simple, and it's called multi-head attention. Instead of doing one massive attention calculation, we take our high-dimensional embedding space and slice it up into smaller pieces. We give each of these smaller pieces its own set of query, key, and value matrices. We call these separate parallel tracks heads. Because they initialize randomly and learn independently, each head naturally specializes. One head might learn to act as a grammar tracker, connecting subjects to verbs. Another head might completely ignore verbs and focus entirely on tying adjectives to nouns. Still another might look for emotional tone. They all read the sentence in parallel, completely independently of one another. Once each head has calculated its own specialized little context vector, we simply stack them all back together, concatenating them into one tall vector. Finally, we multiply this stacked vector by a final output matrix. This mixes the specialized insights from all the different heads back together, leaving us with a single, deeply rich word embedding that understands its exact grammatical and semantic place in the sentence. There is, however, a glaring hole in the logic we've built so far. Because the self-attention mechanism processes everything simultaneously, it completely loses the concept of sequence. To the network, the sentence "dog bites man" and "man bites dog" are just identical bags of words. If we want our model to understand language, we have to find a way to inject time, or order, back into this static space. We do this through something called positional encoding. Instead of just appending an integer, like 1, 2, or 3, to each word, the creators of the transformer opted for a more elegant, continuous approach. They used a combination of sine and cosine waves of varying frequencies. Imagine a series of waves flowing through our embedding dimensions. The first few dimensions oscillate rapidly, while the deeper dimensions wave much more slowly. If you take a vertical slice at any given position, you get a unique mathematical signature, a specific blend of wave values that uniquely identifies that exact spot in the sequence. We take this signature, packaged as a vector, and simply add it to our original word embedding. Geometrically, you can think of this as gently nudging and rotating the word vector in our high-dimensional space. So the word dog at the beginning of a sentence points in a slightly different direction than the word dog at the end. By doing this, we keep the massive speed advantage of parallel processing, but now every single word carries the unique rhythm of exactly where it belongs. So far, we've looked intimately at the machinery inside self-attention. But if we zoom out, this is really just one half of a larger puzzle known as a transformer block. Before moving on, the network takes the original, unupdated word vector and adds it directly to the output of the attention mechanism. This is called a residual connection. It acts like a mathematical safety net, ensuring the original identity of the word isn't lost in the mix, while a normalization step keeps the numbers mathematically stable. Next, each vector passes through a standard feed-forward neural network. If self-attention is the space where words talk to each other to gather context, the feed-forward layer is where each word processes that new information individually. After one more add and norm, we have a complete transformer block. Now, in a real large language model, you don't just do this once. You stack these blocks, dozens of them. Raw tokens enter at the bottom. As they flow upward through successive layers of attention and feed-forward processing, the vectors shed their literal meanings, transforming into increasingly abstract, highly contextualized representations of the text. At the very top, the final vector of our sequence is used to cast out a prediction, generating a probability distribution over the entire vocabulary to guess the next word. It's incredibly tempting to look at modern AI and see a ghost in the machine. But under the hood, there is no magic. It is, from top to bottom, a massive sequence of matrix multiplications, dot products, and shifting arrows. It's a profound testament to the fact that simple linear algebra and geometry, when scaled up to billions of parameters, can seamlessly mimic the patterns of human thought.